One of the traditional standard ways of teaching about circuits and energy and electricity is to start with a circuit like this. And just imagine that as charge moves through the power supply, it gains energy. It's now got more energy here. It moves through the circuit, trundling through the wires. It drops off its energy. Then it trundles through these wires, all the way back to the power supply, where it picks up more energy again. And it's a nice picture, but it actually doesn't help. It causes some problems. Now, it's true that the current is the rate of flow of charge, and we can look at the current at any point, maybe bang an ammeter here, and measure what that current is. And it's true that the potential difference is the amount of work done per unit of charge that moves through a component. So we could bang a voltmeter here, and if we know the current, then we can work out the power, the rate that energy is transferred by that resistor. But the circuit doesn't really help us very much in understanding what's going on. What we need to do is put two resistors, and the problem, well, it reveals itself. How does the charge know, carrying its energy along like this, that it can't drop all of its energy off here? It's got to keep some so that it's got something to drop off through that resistor before returning back to the power supply. Now, when you do the calculation of the average velocity of the charge through the wire, you find it's really, really low. So it's simply not true that the charge is picking up energy and dropping it off. It's simply not true. It's a nice picture. It's a nice cartoon. It helps us understand what's going on. It's not actually how it works. It's worse than that, though. Our cartoon actually makes this much more confusing than it needs to be. And when you get pictures like this, well, forget about it. That's really confusing. How on earth does the charge know that some of it should go this way, some of it should go this way, and how much should go down each branch? How can a charge see ahead and know that there are two resistors here, but only one here? We can make the picture easier and say they're all the same resistance, but still the charge has to know. And there's all sorts of arm-waving ways of trying to explain this, saying that the charge kind of backs up here, so it's harder to push it through, and you've got the forces between charges. And saying that, well, no, we don't have to get the charge back to the cell to get energy. Actually, what happens is each charge pushes on the charge next to it. But even those stories don't really say what's going on. They're wrong. So how are we going to explain it? Well, I've got a different way of explaining it, and I'll explain it in terms of potential. Most people get some idea of potential when they first hear about gravitational potential energy. If I have an object like this pen, and I lift it up, I've moved it through Earth's gravitational field. It has less gravitational potential energy here, and more gravitational potential energy there. Now, all potential energy is the potential divided by the mass. And what does it actually tell us, this potential? It's just a number that just tells us our position in Earth's gravitational field. This is a low potential. This is a high potential. It's just a number that tells us our position in a field. That's all it does. And so when I'm at a higher potential, I have more potential energy because I multiply the potential by the mass. When I'm down here, I'm at a lower potential. If I multiply the value of potential by the mass, I've got a lower amount of potential energy. So you meet potential energy very early on, and you accept it and go, okay, yes, I understand potential energy. You never thought, well, why is it that we gain energy? What's going on here? Well, we're moving through Earth's gravitational field. And when we talk about potential energy, we are talking about moving through a field. Now, in the case of gravity, we can kind of visualize that by way of height. We can see it. Actually, Earth's gravitational field is slightly stronger down here than up here, but it doesn't matter. We're just looking at position in field. And we can see, well, it's actually almost the same, but it is slightly different. But we can see that we're moving through that gravitational field, and if I let go, whoop, we see the pen fall. Of course the pen falls. The pen falls because there exists gravity. And gravity is this field that is pulling masses towards the centre of the Earth. Well, why is that happening? What it's trying to do, this force, is reduce the potential of the mass. That's what it's trying to do. Well, in our circuit, we're going to be looking at the same idea. We're just going to be moving in a field. Here, we have a high electric potential, and here we have a low electric potential. And in fact, the unit we use to measure our position in the electric field is the volt. So here, maybe we have a potential of 0 volts. And here, maybe we have a potential of 9 volts. Well, we can visualize potential in the same way as we visualize height, because gravitational potential increases with height. Well, electric potential, nothing to do with height, because nothing to do with gravity. It's a completely different field. But we can use the same picture in our mind to understand what's going on. If this point is at 9 volts, and there's nothing along here to do any work on our charge, then a charge here is also at the same potential, 9 volts. And this is also at 9 volts, and this is also at 9 volts. At the same potential at all those different places. Now let's just imagine for simplicity, I don't know what these resistances are, but let's just imagine that here the potential difference was, well, let's say, well, not the potential difference, let's say here the potential is 6 volts. It's at a lower electric potential. You can imagine this is a certain height, this is a lower height. And think of it like a roller coaster track. So if we have a branch, a very weird roller coaster with a branch, then these branches have to connect to the same height here, because the charge that comes here will join with the charge that comes through there. So that position might be at 6 volts. Well, what does that mean? Well, that means the potential difference across this resistor is going to be 9 subtract 6, 3 volts. And the potential difference across these two resistors is going to be 9 subtract 6, 3 volts. And maybe they're the same resistor, in which case the potential difference between these two would be 1.5 volts, and the potential difference between these two would be 1.5 volts. What do we mean by potential difference? We just mean a difference in electric potential. Use our height analogy. It's just a difference in position in an electric field. And if this is 6 volts and that's 0 volts, then the potential difference between this, which is also 6 volts, and this point down here, which is also at 0 volts, the potential difference between those 2 points is going to be 6 volts. 6 subtract 0. And what's fascinating, absolutely fascinating, is it doesn't matter which way we go around this roller coaster. If you start here, 9 volts, we drop 3 volts, we're at 6 volts, we drop 6 volts, we're at 0 volts, we pick up 9 volts again. Remember, the potential is analogous to our height, our position in Earth's gravitational field, but it's an electric potential, so it's our position in the electric field. We can't talk about height for that. We don't have a nice, easy picture, but it's a helpful picture to use. If we go this way, we go from 9 volts potential, we drop 1.5 volts, so we're now at 7.5 volts. We drop another 1.5 volts, we're now at 6 volts. And then we go back up here, and so on. So this picture, using heights, I think is quite helpful. This toy is called a gravitrax. It's basically a marble run where you can change the heights of different parts, and as you change the heights of different parts, it gives the ball different positions in Earth's gravitational field, and therefore different gravitational potentials. But you can think of this as being analogous to our circuit, where the height gives us an indication of the electric potential, and this ball is a charge. So if I start up here somewhere, and this is actually 8 units high, that's a potential of perhaps 8, moving along here, that's still 8 units high. That's still 8 units high, but now we drop all the way down. And the reason why we drop is because we're reducing potential. So there's a force acting on us. In this case, it's a gravitational force. In the case of circuits, it's an electrostatic force. But to get up this last part, to get up back up to here, I've got to go 3 units up. So I've done work on my charge, lifting it up 3 units, and then done another 6 or whatever it was, 5 units. I think it's 5 units. I think it's 8 all. So this is like our power supply, lifting the charge up in potential. And it doesn't matter. This charge is at that potential now. It drops down, doesn't matter. We can have lots of charges. I could go into my gravitrax box. I could get lots of charges. It doesn't matter. The charges don't have to push against each other. None of that matters. We just lift the charges up by doing work on each one. That's what the battery does. And then once they've been lifted up, they'll fall back down again. This point's at a certain height and therefore a certain gravitational potential. That's at a lower height, therefore a lower gravitational potential. That's at a lower height, therefore a lower gravitational potential. These are at high heights. So these are our battery of cells, cell 1, cell 2. This is just a wire. It's the same potential, it's the same height. And then resistor, resistor, resistor. There's a series circuit. But what if we had a branch? Well, the gravitrax allows us to have branches. Well, let's put some branches in. Well, I'm going to move back a little bit to see all of my branches, but there we go. We've now got our horizontal wire here. We've got our cell, just like we had before. These are rising in height. And then we go down here and there's a branch. The charge could go this way, or it could go down in these 1, 2, 3 stages. This is like 1 resistor, and this is like 3 resistors in parallel. Well, they're series with each other, but in parallel with this resistor. And you could have charge being lifted up and then dropping down and going, well, charges can't leave the wire. So let's go a little bit slower. Okay, go a little bit slower. Let's imagine that they've got some energy, they've dropped down to there and they go this way. They can go that way, or we can lift up our charge and it can go the other way instead. It could go either way, it doesn't matter. It doesn't matter which way it goes. Now, the reason why more of them go one way than the other, well, we can talk about that in terms of Kirchhoff's laws later. It doesn't matter. Our picture of what's happening with energy is quite clear now. Work is being done to move the charge up a potential. There's something there to stop that flying off. Work is being done on the charge to lift it up in potential. Then it goes like that. Then work is being done to lift this charge up, and it goes down like that. And it can go different ways. This is actually switching, and it wouldn't be switching 1, 1, 1, 1. Wouldn't be necessarily like that. And, that's a little bit more complicated. The reason is to do with what's happening with the field around here. That's all it is, the field. This charge has no idea what's coming up. No idea. It's not picking up energy and deciding where to drop it off. It's just falling through electric potentials. Let's see if we can get some better views. So there's our high potential, dropping to a lower potential, and then we're dropping down there. All the way down to this is the lowest potential. Notice it doesn't actually have to be 0, it's just the lowest potential. And then we go up 3 potential units, then up another, I don't know how many that is, 4 potential units. Then we stay at those higher potential, and then we drop back down again, decide to go a different way. That's a parallel circuit. And if you think about it in terms of electric potentials, and potentials being analogous to heights in a roller coaster, it's much easier.